Hello, I'm Dr. Joe Keating. This is How Do You Solve a Problem Like Morphology, Part 2. Welcome back. Last time we talked about the different methods you can use to estimate phylogeny from discrete morphological data. In this lecture, we will compare these different methods and try to ascertain which of them is the most accurate. There are two ways we can gauge the performance of different phylogenetic methods. These are empirical studies and simulation studies. For empirical studies, the data consists of discrete character matrices coded from real morphology. These datasets should contain real phylogenetic signal, including nuances and peculiarities that would be difficult to simulate. That said, the data was collected by imperfect humans and could be subject to biases related to taxon and character selection. The biggest drawback for empirical studies is that we can never know the true tree with any certainty. As such, we can't measure the accuracy of different phylogenetic methods directly. Instead, we must use a proxy for accuracy. In contrast, the simulation approach allows us to define a true tree, against which we can measure accuracy directly. The downside of the simulation approach is that the results are only applicable to the real world if the simulations are realistic. For example, if I were a traffic planner and I was trying to decide the cheapest and most efficient type of junction to build, I could simulate traffic flow over different junction types based on 1,000 cars passing every hour. The results of my simulations might be fairly applicable to a busy city, but would be completely inappropriate for solving traffic issues in a tiny village. As you can see, both empirical and simulation approaches have inherent advantages and drawbacks, so it's worth considering both. Let's start with empirical study. For empirical study, we need independent data that we can use to compare the trees produced by different phylogenetic estimation methods. One such source of data is stratigraphy. It has long been understood that the stratigraphic distribution of fossils provides information about phylogeny. If the fossil record were perfect, the stratigraphic distribution of fossils would mirror their branching order. As we know, the fossil record is far from perfect and is subject to taphonomic, environmental, geological, and collection biases. That said, we may still expect the true tree to have a reasonable stratigraphic congruence. Consequently, given a choice between competing tree topologies, we may prefer a tree topology that is congruent with stratigraphy over a topology that is incongruent with stratigraphy. There are a number of different indices that can be used to quantify stratigraphic congruence, including the stratigraphic consistency index, the gap excess ratio, the relative completeness index, and the Manhattan stratigraphic measure. In order to compare the stratigraphic congruence of different morphological phylogenetic methods, we first need a published morphological matrix and associated stratigraphic data. We then estimate a tree using each method and measure the stratigraphic congruence of each tree using our chosen stratigraphic congruence index. Individual empirical datasets may be subject to biases or errors. Consequently, we should repeat the analysis using many independent empirical datasets. We then compare the distribution of congruence scores for each phylogenetic method. This approach is known as a meta-analysis. This is exactly what Rob Sansom, myself, and colleagues at the University of Manchester did a couple of years ago. We compared the stratigraphic congruence of most parsimonious trees and Bayesian posterior trees for 167 empirical tetrapod datasets. We found that most parsimonious trees had, on average, higher stratigraphic congruence than Bayesian posterior trees. The difference in congruence was small, but significant. There are a couple of reasons why this might be the case. Firstly, most parsimonious trees might be closer to the true tree. Alternatively, our empirical data may be biased. All of the character matrices we analysed were originally constructed for the purpose of parsimony analysis. It is common practice to analyse a morphological matrix during its construction. This is called data peaking. Because of data peaking, researchers may have consciously or unconsciously biased their data to ensure that it was stratigraphically congruent. Recently, April Wright and Graham Lloyd have reanalysed this data. They show that Bayesian posterior trees tend to exhibit much greater variance with respect to stratigraphic congruence compared with most parsimonious trees. Although posterior trees tend to have a lower mean stratigraphic congruence, for some datasets, they also contain the most stratigraphically congruent estimates. So, to summarise, most parsimonious trees have higher average stratigraphic congruence than Bayesian posterior trees. However, the Bayesian posterior may contain trees that are more stratigraphically congruent than any of the most parsimonious trees. These empirical studies do not clearly support one method over another. Perhaps simulation studies will prove more informative. In order to produce simulated morphological data, we provide a fixed topology representing the true tree. First, we simulate character changes on the tree using an evolutionary model. We then estimate trees from the simulated data using different inference methods. Finally, we measure the accuracy of our estimated trees against the true tree we used to simulate the data. We repeat this hundreds of times so that we can compare distributions of accuracy scores between methods. There are a number of different metrics for comparing the topology of two trees. Robinson folds, or RF distance, is defined as the sum of unique bipartitions for two trees. Both trees in this example have 3 unique bipartitions, giving a distance of 6. We can also use bipartition comparison to measure accuracy. The estimated tree has 5 bipartitions, of which 2 are shared with the simulated tree, giving a percentage accuracy of 40%. Another distance measure used to compare trees is the subtree prune and regraft, or SPR distance. This method is so called because it involves pruning a branch and regrafting it elsewhere on the tree. The distance between trees is merely the number of prune and regraft moves required to transform one tree into another. In the example below, our estimated tree can be transformed into our simulated tree in a single prune and regraft move. Although this method is quite intuitive, it is mathematically difficult to work out the maximum possible SPR distance between two trees. As such, we are not able to express the SPR distance as a percentage accuracy. Another useful tree distance metric is the quartet distance. Quartet distance is defined as the number of different 4 taxon statements, or quartets, between two trees. To compare quartets, choose any 4 taxa in your tree and compare their topology. In the example below, you can see that, if we imagine straightening out the branches without nodes, these quartets are identical. In contrast, these quartets have different topologies. Our estimated tree has 70 quartets, of which 45 are shared with the simulated tree and 25 are different, giving an accuracy of 64%. Note that quartets and Robinson-Folds metrics yield very different accuracy scores. This is because the Robinson-Folds metric is especially sensitive to rogue taxa. A single branch that is resolved differently in two trees can result in a large Robinson-Folds distance. The quartet metric, on the other hand, is less biased by rogue taxa. It is also important to note that precision influences all tree comparison metrics. To use bipartitions as an example, the RF distance between the trees below is 4. Our estimated tree has no unique bipartitions, while the simulated tree has 4 unique bipartitions. Our estimated tree contains only a single bipartition, yet that bipartition is also found in the simulated tree. As such, the estimated tree is 100% accurate. All of its bipartitions are found in the simulated tree. However, a tree with a single bipartition does not contain much information about the evolution of its taxa. Consequently, when assessing the accuracy of trees, we must ensure we do not also reward imprecision. In 2014, April Wright and David Hillis published a study on the performance of Bayesian inference and equal weighting parsimony on simulated morphological data. They simulated characters under the MK model using a previously published tree based on empirical data. Their results suggested that Bayesian inference was more accurate than equal weighting parsimony. In 2016, Joe O'Reilly and colleagues from the University of Bristol criticised the Wright and Hillis study for simulating data under the MK model, because the same model was used to estimate phylogeny under Bayesian inference. They suggested this may bias the results in favour of Bayesian inference. O'Reilly and colleagues repeated the study using a modified version of the HKY molecular model to simulate morphological characters. They filtered their simulated datasets to ensure they contained a realistic amount of homoplasy. They estimated trees using Bayesian inference, equal weighting, and implied weighting parsimony, and found that Bayesian inference outperformed both parsimony methods. The following year, the same authors, this time led by Mark Puttock, expanded their study, this time simulating data on perfectly symmetrical and asymmetrical trees in order to consider the effect of tree shape on accuracy. They also tested maximum likelihood estimation for the first time. They found that Bayesian inference was more accurate than all other methods, but at the cost of precision. This study caught the ire of Joseph Brown and colleagues, who pointed out that if you consider the support of maximum likelihood trees via resampling and collapse bipartitions under a certain threshold of support, maximum likelihood estimation can achieve a similar level of accuracy to Bayesian inference. Building on their previous studies, O'Reilly and colleagues then conducted a further study in which they incorporated resampling for maximum likelihood and parsimony estimation. They found that probabilistic methods that take uncertainty into consideration were more accurate than equal weighting parsimony. Pablo Golubov then entered the debate. He criticised the simulation procedure of O'Reilly and Puttock. In particular, he suggested that probabilistic models, which simulate data under a constant rate of evolution, may be biased in favour of probabilistic inference methods that assume the same. He also suggested that the distribution of homoplastic characters in O'Reilly and Puttock's simulations was unrealistic. Instead, Golubov simulated data under a random model of character evolution, with no assumption of a shared evolutionary rate. Simulated datasets were constructed so that they possessed a realistic distribution of homoplasy. Contrary to previous studies, Golubov's results suggested that implied weighting parsimony was more accurate than all other methods. Pathak and colleagues responded to Golubov's criticisms in a 2019 paper. Firstly, they pointed out that Golubov's realistic datasets were actually heavily skewed towards characters with low homoplasy, which may have biased his results in favour of implied weighting parsimony. They simulated data using a procedure analogous to Golubov's method and filtered the datasets by their homoplasy. From their results, they made some fairly nuanced conclusions. When datasets have low homoplasy, all methods have comparable accuracy. However, when datasets have high homoplasy, Bayesian is more accurate than standard maximum likelihood and parsimony trees, and more precise than maximum likelihood and parsimony trees with resampling. Finally, Martin Smith applied the quartet's distance metric to the problem in 2019. Using previously published simulated datasets, Smith measured the number of correct, incorrect, and unresolved quartet statements in estimated trees with different levels of resampling. He concluded that both Bayesian and implied weighting parsimony with resampling can produce trees with similar levels of accuracy and precision, and that both of these methods can outperform equal weighting parsimony. Clearly, there is a lot to consider from these simulation studies, as well as a lot of conflicting results and disagreements. However, I think we can make some general conclusions. Accuracy is related to precision. Methods with more precision, for example, implied weighting parsimony and maximum likelihood, tend to have lower accuracy, while methods with less precision, for example, Bayesian inference and parsimony or maximum likelihood with resampling, tend to have higher accuracy. This is related to whether or not we consider topological support. If we ignore support, our estimated trees are precise, but contain poorly supported relationships that may be inaccurate. On the other hand, if we collapse poorly supported branches, estimated trees are less precise, but may be more accurate. Finally, there is some indication that Bayesian majority rule consensus trees seem to possess a desirable balance of both precision and accuracy. Hopefully, you have also noticed that there is substantial disagreement in the field as to what constitutes a realistic morphological dataset. We will consider this more carefully in the next lecture. For more information on empirical and simulation approaches to assessing the performance of morphological phylogenetic methods, please have a look at the following references.